Hello everybody. Welcome to 2024. Yeah, we are resuming the Africa Women in Algebra online series. Yeah, and today's speaker is again Dr. Foluke Usamot from University of Ilorin, okay, in Nigeria, and she's a lecturer there at the Department of Mathematics in the Faculty of Physical Sciences. So she is her area is in functional analysis, yeah, I think. Yeah, and then so her topic today would be on fixed point results on semi-groups of order preserving maps in metric space. Okay. So Dr. Idayat, the floor is yours, and welcome. Thank you.
Thank you very much. Good afternoon, everyone.
Good afternoon.
I'm Dr. Idayat Foluke Usamot. I'm a senior lecturer at the Department of Mathematics, University of Ilorin. I'm here to present a research seminar titled Fixed Point Results on Semi-Group of Order Preserving Maps in Metric Spaces. This seminar talk examines closely the existence of fixed points on semi-group of order preserving full contraction, denoted by OCTN, and contractive, denoted by OC*TN mapping in metric spaces, under the necessary condition that the images of the semi-group at certain points are comparable to the deterministic fixed points. And some examples were given to validate our results. Here, we work on nonlinear operators, which is an important research in nonlinear analysis. Then Banach contraction mapping, basically all its theorems were generalized by many researchers. Some generalize it using arbitrary distance functions, and some generalize it using weakly contractive conditions. So in this seminar, we establishes the existence and uniqueness results of fixed point theorem on OCTN and OC*TN, that is on order preserving full contraction and order preserving full contractive in metric spaces, where in literature no work or little work has been done. So however, the notion contractive in semi-group connotes non-expansive in metric spaces. Although we are going to show some examples that illustrate this, our assertion. So we have the definition of fixed points represented by equation 1, and we define the waist as the maximum of the image of our phi theta and the minimum of the waist as the minimum of the W, that is omega minus phi theta. So we equally define the order preserving full transformation semi-group, which is denoted by as that set, and we have the definition of other full transformation semi-group, which is contraction and contractive, illustrated as the equation 2 and equation 3 respectively. Then we have some definitions from literature. That is definition 1.1 is the definition of full contraction mapping itself in metric space, where our K here is strictly less than 1, which represented by the equation 4. Then we equally have the definition of non-expansive mapping, which is illustrated by the inequality in equation 5. Then we have our definition, which is definition 1.3, which is the definition of order preserving full contraction map in metric spaces. And that's our operator T defined inside that our order preserving full contraction mapping must satisfy the two conditions stated in definition 1.3. We equally have another definition, which is 1.4, which is the definition of contractive mapping. We have contractive mapping in semigroup, but in this case, contractive mapping is equally now not expansive in complete metric space. So we need to transform that's our elements in semigroup, that is other preservable contractive mapping, into a space in a complete, which is complete metric space. It must complete before we can have results. So theorem 1.5 is equally a theorem in the literature which talk about the non-decreasing and non-increasing. That is the weakly contractivity condition of our Banach contractive theorem. So we usually make use of lemma 1.6 in our result, which is which define the Cauchy sequence in a certain space. So we now go straight to my main result. We start by looking at the lemma 2.1, which is a small result. So every mapping in OCTN, that is other preservable contraction mapping, are what? Are contraction. While every mapping in OCTN are non-expansive in a complete metric space, E, rho. For that, our E contained in R. I said earlier that the major work here, we try to compare results from a fixed point in our semigroup that we all know to another deterministic fixed point in metric space. I saw you need to change or transform all those our elements in semigroup to a point in a space before we can carry out our research, which are the most difficult aspects of this work, because it's not too that easy to transform our elements into a space. So example 1, we consider the finite set which ordered in standard way, which is a transformation. Then we now consider a mapping, that is a contraction mapping. The normal contraction mapping we generate from our full contraction. So on that note, we have our mapping in OCT2, that is when our n is equal to 2, corresponding to fixed point theorem. Now we need to transform those points, that is our elements in OCT2, to another problem in fixed point, that is we transform it to a problem, that is to a function using an operator. So that operator we have here is T, which is T of mu now equal to mu square minus 2 mu plus 2. It is exactly that our transformation we have in the semigroup that we transform into this, in order to have compare the results. That is, we know that from this our mapping in semigroup, we have our fixed points here to be 1 and 2. That is 1 map to 1. If you look at the mapping there, you see that for our phi theta, which is equal to, I just wrote that in a circle form. That is 1 map to 1 and 2 map to 2 in OCT2, which now corresponds to our fixed point problem, C of mu equals half square minus 2 mu plus 2. It is this same element that I later transformed to this fixed point theorem problem, in a complete metric space. Remember I said that before we can do anything based on Banach fixed point theorem, he stated his theorem in a complete metric space. So obviously, if you look at that our mapping, you see that it's a contraction, because 1 map to 1, 2 map to 2. Based on the definition of contraction, that is the image must less or equal to the point. So on that note, we want to now say that this same contraction in semigroup is also contraction in a contraction in metric space. That is what we try to do here. So on that note, we see that from here, contraction mapping, we need to now use our definition of a contraction mapping, we stated earlier, that is in equation 4. So now define our space, because we need to define our space. We define our space by the operator T to be this half comma this map to this, which is a self map. Then now using the definition of contraction in metric space, which is row of this metric. We take the metric of this and we discover that from here we have it to be less or equal to this k row of this, that is metric of this mu comma phi. And if we, by the end of it, we see that our k here is strictly less than 1, we satisfy the condition of contraction mapping. So on that note, we now say that this our operator T we define here is a contraction mapping in a complete metric space E comma rho. It is a complete metric space, but those points of our mu and phi belong to this space we defined. Then we also take a look at the second example to show that every contractive mapping in this particular OCT static, that is order preserving full contractive mapping, we consider it in T3, in full transformation 3, when n is equal to 3, is now a non-expansive in a complete metric space. So we use the same approach by now still transform all these our elements here. If you look at this one, you see that we have fixed points, 1 map to 1 here, 2 map to 1, and 3 map to 3 in OCT3. Then we want to convert this our elements into a element, a point in a space. On that note, we need to first define our space, which is this is our space, and then we now derive this our function. We define the operator as this, which is mu square minus 3 mu plus 3. So if you look at this, the fixed point here is also satisfy what we have here. Then we want to show that it also satisfy the condition of non-expansive in a metric space. So we see that clearly this mapping of this semigroup is a contractive in a semigroup, and it is satisfied equation 3. Then we now take the metric of this our operator, and eventually we see that we don't have, this is one Letizian mapping, that is, we call it non-expansive as well. So we are able to show that every contractive mapping in full transformation semigroup is equally obeyed, is not expansive in a complete metric space. And that is our first result, which is lemma 2.1. So we have this lemma 2.2. Say let this be E comma rho be a metric space. This is also a complete metric space. They will now say that every sequence there corresponding to this operator T in OCTN is monotone increasing and hence convergence in that our space. So we have this theorem 2.3. So let this space be a complete metric space. T is a correspond self-map or further preserving full contraction. We satisfy this equation 6. This one is a weekly contrast mapping, weekly contraction mapping, and we now define this our waste. This is the maximum of the waste as this. We express it as this. This our waste, we define it before in the semigroup. We define it as maximum waste and minimum waste. But in this case, we try to expatiate it more by having it as maximum of any of these sets here. So together with this shelter as stated in theory, which is this shelter is just a control function that we use over this our set, this all these points here, which is stated in theorem 1.5. For every these points defined in this space, they want to prove that this particular operator T has a unique phase point. On that note, we need to first take the initial guess, which is mu naught, and that's our space, and we define the sequence mu n. Then we also need to define the iterative sequence, which is chi of n is equal to this operator T mi of n minus 1. Then in that case, if there is a positive integer, that is, it is our fixed point, the definition of our fixed point is defined as, that is, T of sigma must equal to sigma. That is the fixed point. Then we now say that sigma is a fixed point of T. Now we want to prove by contradiction that, assuming that this our sequence is not equal to this sequence for n greater or equal to 1, then from condition 6 stated earlier, that is from that our inequality stated earlier, so we need to now substitute this our iterative sequence using it to now expatiate that our inequality in equation 6, to show that our equation inequality is Cauchy. So, and that is what the steps we took to this place. Substituting all those things, values there, point there, we are able to expatiate to this place. And since the self map, which is defined in this other preserving full contraction map, and by virtue of our lemma 2.2, which says that every sequence there is a monotone increasing, we have this inequality to hold. So we now obtain this. Since this inequality hold, then we now obtain this inequality by substituting. Since this one is less or equal to this, then we make use of this by re-expatiating it to this one, and that is that theta of the row of, that is metric of this, is less or equal to 0, implies that this particular one is less or equal to, which means that the theta n is equal to, that is the sequence of this is equal to mu n plus 1, which is a contradiction. You know, if you recall the statement we made at the beginning, so it is a contradiction. So also by lemma 2.2, we have this inequality, that is the metric here is less or equal to the metric here for all n greater or equal to 1, and then there exists d greater or equal to 0, such that the metric between this sequence is equal to d as n tends to infinity. So we now have taken the limit as n tends to infinity, the above inequality, and we now using the continuity of theta, which I said is a control function. We have this inequality, which is odd, which implies that d is equal to 0, and hence the metric between this sequence is tends to 0 as n tends to infinity. So suppose this sequence is not a Cauchy sequence, then for every for any epsilon greater than 0, so you can now choose monotone non-decreasing sequence with this psi k greater than k and the n of k greater than k for all positive integer k, such that this inequality 8 and 9 holds. So from 8 and 9 by triangle inequality, we have this our inequality 10. Again, for k greater or equal to 1, we now have this metric between this sequence with less or equal to metric between k. Now taking the limit as k tends to infinity in this inequality, then by lemma 1.2 gives this inequality 11. So from 6 and 7, it now becomes the metric between this particular sequence now equals to this. So now less or equal to, we go back to our inequality stated in 6, and by the condition 7 of it, we substitute it back and have this inequality. So at the end of it, by now letting this particular k tends to infinity in this particular inequality, and by lemma 1.6 and by 10, and also by the virtue of this control function, have this one holds. So this implies that the theta of epsilon is equal to 0. And hence, this sequence is a Cauchy sequence, which we are trying to show. So also from 6 and 7, that is the condition 7 of it. So we have this inequality, which is that is the, if we take the metric between this, we give us the inequality here, which is also equal to maximum of the set of all the sequence inside it. And by taking the limit as n tends to infinity in the above inequality and using the continuity of theta, that is our control function, this particular inequality will also hold, and which means that this metric of this is our fixed point we first define, that is sigma comma t operator sigma will equal to 0. And once the metric of this is equal to 0, it shows that sigma is equal to operator sigma, which is our fixed point. So hence we hence prove that sigma is a fixed point of t. Next, we want to show that that fixed point is unique. So we now define another fixed point, sigma star. We try to define another fixed point in T, that is for that our operator T. And we now want to show by contradiction that suppose that our fixed point sigma is not equal to another fixed point sigma star, then from that our condition inequality 6, and that's our contractive condition there, this inequality will also holds. Now consider it taking the maximum of all these sets after substituting all those our points. Then we discover that by virtue of our this control function, discover that our fixed point is also equal to sigma star, which is another fixed point. So which shows that the fixed point is unique. Now let's take a look at the corollary. So which we deduce is just what we deduce from our theorem, above theorem. We have our complete metric space E comma rho, and we also define the operator T, which map E to E, which is a self map, as I said earlier. So, this from the generalized order preserving contraction mapping. We want to generalize the result now, such that for all these points here in this space, this inequality holds, where this our maximum of the ways is as defined in 7, which was earlier started. Then there exists a unique fixed point. So it means that we want to generalize all the elements of full contraction so into the space, that is into metric space, complete metric space. Then the proof of this is by letting this our omega bar equal to high, that is the identity mapping on this space. Then I'll follow the analog of all the theorem 2.3. You see that we are going to have the same result. Now we take a look at example under this, where we have theta to be a transformation in OCT, and that's our usual mapping, that is which define that we take the set in T3, that is from this one map to this, and we have our mapping of this form. In this case, only fixed point we have here is 1. No, it is 1 map to 1 and 3 map to 2, 2 map to 1, which is equivalent to our fixed point problem. You know, remember I said that the problem we have with this work is how we are going to transform all these our elements into a space. That is the problem we always face before we can transform. It's not too that easy to generate it. So here we have our function defined this way. And if you look at this one, the only fixed point we also have here is 1. And if you look at the fixed point we have in semigroup here, it's also 1. So it shows that the fixed point in semigroup here is equivalent to deterministic fixed point in metric space, and where T is a self-map defined in this particular space. So also, let's he be endowed with the usual metric. We want to show that it satisfied now that our contractive condition defined in equation 6 and 7. So we have usual metric to define this way, and we define this our omega bar of T to be this, which is also a control function defined in our theorem. And this our another control function theta, also defined as AT for this condition of A, that is our A is also strictly less than 1, and we define this our T here. We define this T here also strictly equal to 1. You can take that from 0 to 1, and the mu less than all the points we have here for this one in that our space. So obviously you see that this operator T is a contraction mapping for this metric less or equal to this, and our K is always strictly less than 1. For this to be contraction mapping, this particular K here must strictly less than 1. So now let's our mu be 1. We want to substitute some points into this our inequality to show that it is surely a contraction mapping, and having our this point V to be 2 and A to be defined as 1/4. Then by 7 we have this one. We want to take the maximum of those points from here and now substitute it back into our inequality in 6. And when we substitute all those values we have there, taking the metric of them, we see that the omega bar of 0 is equal to 0, and omega bar of 1 is equal to half, and the theta of 1 is equal to 1/4, which means that this operator T satisfies contractive condition 12. So more so, if you now choose this our initial guess, because we need to choose we want to check here that it is a convergent, because before we can have fixed points, this condition must hold. That is, this operator, that is the derivative of this particular this operator acts with this initial guess must less than 1. So if you have this result, that is, if this inequality holds, it means that we are going to have result. This our function here, we converge to a particular fixed point. So this implies that T converges. That's the first thing we need to do before we can even start our iterative process. Then define iterative sequences. Since we already confirm that this surely converge, then we can now start our iterative sequence using the Picard iteration. So on that note, we have this one. By the time we have our N1, which is our first iteration, which gives us 1.055, T iteration 12, so where we now have our 1.000, which is the deterministic phase point. And this is what we want to compare, because if you look at from the mapping up, I said that the only phase point we have here is 1. And at the end of the day, based on that our problem transformed into phase point, we equally have our deterministic phase point to be 1. And this shows that T has a unique phase point, which is now comparable with the deterministic phase point in a complete metric space test. Again, we have the remark. This contractive condition 6 and 12 with respect to 7 holds for example 2. Example 3, when T is defined in OCTN alone, when it is only contraction, but phase when defined it in OCT star, that is order preserving full contractive mapping. So we're going to take a look now as another theorem now in contractive mapping. So we define our operator T, which is also a self map, in OCTN and OC star TN, such that for all these points here, this inequality holds, where this our metric, that is the maximum of the set here, is defined in 7. Then there exists a unique common fixed point, say sigma in E, such that this condition is holds. Now let's take a look at the proof. We equally need to define the initial guess, which is arbitrary points, and we need to construct the sequence to show that is our sequence is Cauchy, because before we can have our results, that's our sequence must, I said that must be a complete metric space. It means that the Cauchy sequence must converge into the space we defined. That is why we need to first carry out that is a Cauchy sequence. After we first check whether it is Cauchy, then we now say that it is complete. Those are the first two steps we need to check. So once it is Cauchy, we later now check, is it complete in that space we define? And we took the first step. But now consider different mapping here. If you look at this one, we choose one iterative sequence and another one to prove our result in this case. So start from 7 as well, equation 7 as well. We substitute for all those our point there. That is the iterative point we define. And at the end of the day, we are able to show that it is Cauchy. The same procedure we followed in theorem 2.1. That's what we also did in theorem 2.3. So on this note, we have our result. That is, we are able to show that that's our fixed point taking a different iterative sequence. We also have a unique result, coupled with all those our control function we defined earlier. So suppose there exists another point. Equally, you want to show here that the fixed points are unique, and that is what we did. Even if we try to define it using another operator, and we still have the same points that are fixed with those second operator, and eventually we are able to show that our fixed points are equally unique. So we use this example 4 now to buttress our theorem 2.3. Consider the mapping, this mapping in this contractive mapping, and we define another mapping, which is 1 map to 1, 3 map to 2, and 2 map to 1. In this case, we have 2 fixed points, 1 map to 1 and 3 map to 3. And we still have another one. All of these defined in OCT3. Then with fixed point problem days, we try to transform this particular one into this fixed point problem, and this one into this fixed point problem. Let's see where self map defined as interruption. Hello. Hello. Can you hear me?
Yes, we are with you.
Yeah, now I can. Now we can hear you. You were lost for a few seconds there.
So we have these two operators now defined, which are two self map defined in this space. So thus we show that this operator Q and T satisfies condition 13 with respect to this condition stated in 7. And since mu is less than, I said that the points, they are ordered in standard way. That is, this one is less than this. So we now let our mu equal 1 and v equals 2, so that the metric between the two, if you look at this, the metric between these two, it give us 1. The metric between this operator, we need to substitute. It's not something that, but we have it to be 1. We need to substitute into our problem defined here. And the metric between this as well is equal to 1. And the metric between this is equal to 0. The metric between this is also equal to 0. And metric between this is equal to 0. And again, define this, the one that we use to generalize it, and this control function as given in example 3, and we have this omega bar 0 to be 0 and omega 1 bar 1 to be half, and this control function 1 of 1, that is theta of 1 to be 1/4. So clearly the two mapping satisfy the contractive condition 12 and 13. Hence, you now say that the fixed points of both Q and T are comparable with the images of this faceta contained in this other preserving full contractive, and for this one defined in other preserving full contraction mapping, both defined when n is equal to 3, that is in T3. Now we look at corollary 2.7. Here we want to see generalize the results in theorem 2.6. Let E, that is, let this be a complete metric space, that is E comma rho, and let these two operator such that this map to be two self map, such that for all these points in this space, this inequality holds. Where this one is as defined in 7, then we show that this Q and T have a unique common face point. So the proof of this is also making this to be an identity mapping in the first and second coordinates of theorem 2.6 and follow its analog. Then the result follows. You only have the mark 2.8. The contractive condition 6, 12, and 13 with respect to 7 holes on any two associated mapping in both OCTN and OCT*TN. So we arrive at the conclusion. In this work, we have shown that every images of phi theta, that is of any mapping, which are fixed under the action of the semigroup at a certain point are unique, with fixed points of T in a complete metric space. Also, we have this operator T is not expansive in metric space if the transformation, that is, this particular transformation is contractive. That is, if you have this mapping in other preserving full contractive and we say that it is closed, otherwise it is elliptician for L greater than 1, as discussed in example 3. So more so, any two mappings in other preserving full contractive and other preserving full contraction mapping have images which are comparable with any two self maps in a complete metric space as analyzed in example 4. So the key features in this fixed point theorem is that the contractivity condition on the self map is weakly and only assumed to hold on elements of some semigroup of other preservable contraction and contractive mapping in metric spaces. Thank you for listening. These are my references.
Okay, thank you, Dr. Idayat. Is there anyone with questions or comments for her with regards to this particular